Bismillahirrahmanirrahim. Greetings. This is going to be the third lecture in a series of video lectures that I'm uploading to discuss about the concept of inverse functions. Now, all these video lectures, I'm presenting them at the college algebra and pre-calculus curriculum level, but students taking calculus, freshman calculus, and also high school students can benefit from these lectures. And I strongly encourage you all to watch the entire series. Also, in my channel, you're welcome to watch other videos that are all related to freshman, sophomore level mathematics. Now, in each video, I also provide the site link of the previous one in the comment section for your reference. Now, in this video lecture, I'm going to discuss about the inverse of polynomials of degree 2, and the simplest one is y equals to x squared, which is also known as parabola. So let's get started, shall we? Now, we are all familiar with the graph of a polynomial, the geometrical graph of that. Now, this is a 2-to-1 function. 2-to-1 function. Now, for instance, when x is 4 and x is minus 4, they both have the same value of what? Of 16. So we call it 2-to-1 function. Now, the inverse of this function, because this function is not 1-to-1, the inverse of that will not be a function. It's a relation, but it's not a function. But in the language of calculus, we said the inverse of that is not a single valued function. But that is the word you will be hearing when you take the calculus. Single valued function and multi-valued function. But in the language, in the freshman college algebra and pre-calculus, also in high school, we just say it's not a function, the inverse of that. Now, graphically, geometrically, we are already know how to find the inverse of that by rotation and reflection, and we are going to learn it another way also to do it. Now, what did we do? We pivoted in the origin, then we rotated 90 degrees clockwise or counterclockwise, and then we reflected that one, and that will be the graph of the inverse of that. Now, the paper I'm using is thin, so he shows the other side of it, so you can see that. Is that right? This is the graph of that. Now, in high school, we have heard it that they say vertical line will fail. It hits it more than 1 point. So if the vertical line hits the graph, the geometrical graph of a relation in more than 1 point, we say that is not a function. In this case, we say it's not single valued function. Okay. Now we go to now what we can do so that the inverse of this 2-to-1 function is also a function. Let me put it up so that you can see it one more time. What we can do to make it to be the inverse of that is also function is to restrict the domain of this function. So the domain is all non-negative number, 0 and positive. So if we do that, then this part of the graph will be going to be ignored. Is that right? This part, and then we will be dealing with this part of it. Now look, if I rotate and reflect, you will see that the inverse of that will also be a 1-to-1 function. Will also be a function. In other words, that you are familiar with the vertical line will pass. Now, this is the graph of the geometrical graph of y equal to x squared, restricted, the domain of that restricted to the non-negative numbers. Now, look what I will do. I will rotate it about the origin and then reflect it the whole plane, and look what I will see is transparent. And this is not, the vertical line will pass it, will hit the graph in 1 and 1 point. Because the graph, the domain was restricted, and the graph was what? Was end up to be, the original graph was one-to-one function in a sense. Okay, now let's go and see how we can change the rule of correspondence between x and y, and what we can come up with that, because the goal is for the inverse of that. Is that right? Now, here, y equal to x squared, if I take a square root of both sides, or raise both sides to the power of what to the power of 1/2, I get this one, y to the 1/2 equal to x. Is that right? You can see that. Now, these two, they are the paraphrase of one another. They are synonym. Now, as you can see, they have same graph. Now, this one we are already familiar. We have seen it and we have talked about it. So let's talk about this one. Doesn't matter if you consider assigning value for x finding y or y finding x, this graph comes out of it. This analytical graph. This chart will come out of it. Now look, when x is 1, y is 1. When x is 2, y must be 4. Because the square root of 4 is 2. The principal square root of 4 is 2. As we can see, when x is 2, y must be 4. Because the square root of 4 equals to 2. Now when x is 9, for example, x is 3, for example, y must be what? Must be 9. Because principal square root of 9 is 3. You can see that. So it doesn't matter if you assign values for x and find y, or assign values for y as find x, the very same chart comes from it. Do you follow me? So then what is the difference? What is the difference? They have same graph. They must have same geometrical graph. So let's see if this is the case. Now look at this one. This is y equal to x squared. Y is a function of x. When x is 2, the arrowhead can show it. You can see that? The arrowhead goes up, and here when x is 2, y is 4. When x is 3, y is what? Y is 9. You can see that. Is that right? Now, this one does exactly the same thing, but it starts from 9. So he says when y is, start from y, excuse me. When y is 4, you see the arrowhead? It goes here, x will be 2. So if we want, when y is 9, x will be 3. So it doesn't matter if you select points here and sketch the graph, or if you select points here and sketch the graph, the sketch of graph will be the same. So these two are what? Are paraphrase of each other. They are identical, in fact. I shouldn't even say paraphrase, they are identically same. Okay, now let's see what happens if we change, but we interchange the rule of correspondence between x and y. We interchange the rule of correspondence between x and y. So the first one was y equal to x squared. So when we change the rule of correspondence between them, then x becomes to y squared. Y equal to x squared, interchanging the rule of correspondence, x equal to y squared. Now let's look what happens to the analytical graph before we go to geometrical graph. That we call it sketching the graph. Now look at this one. Again, this one we are very familiar. I don't have to go through and repeat and again. No, I'm changing the rule of correspondence between x and y, and look what happens. These two, for example. When x is 1, y is 1. When x is 4, you see that? When x is 4, y must be 2, because 2 squared is 4. When x is 9, you see that? Y must be 3, because 3 squared is 9, and so on and so forth. Now, look at this chart, or this graph, analytical graph, and look at this chart, or this analytical graph. You can see that x and y are what? Are interchanged. You can see that for yourself, is that right? So x1, y1 becomes what? y1, x1. x2, y2 becomes y2, x2, and so on and so forth. You see that? We talked about it in the previous lecture. Now, let's see, let's sketch the graph of them. Sketch a graph of them in the same plane so that we can see and we can kind of contemplate about the any possibility of difference between them. Now, this we are familiar with. We restricted the domain of y equal to x squared, and this graph came out of it. It's a nice looking one-to-one function. So the inverse of that we are expecting to be also a function. Now, we have already shown by reflection, by rotation and reflection, this is going to be the graph of that. You see that? Now, if we do that, we plug points, x is that, y is that, x is this, y is this, x is this, y is this graph comes out of it. Do you follow me? Now, what I will do next, I am going to pull this one or push this one to come this way so that the y, the vertical coordinate of this graph, to superimpose on the vertical graph of the vertical axis of this graph. You follow me? So, you know, it's good. This is very nice to do, demonstrate that using animation. But unfortunately, I don't have the art. I don't know the art of animation. It's my plan to learn it someday. But sometimes 3D demonstration is as good, if not even better than animation. So I'm going to push this one to come here, and look what happens to that. This graph will come. You can have a good imagination in your head, huh? Can you imagine how the graph will look like? I'm going to pull this one so that the vertical axis of this graph will superimpose on the vertical axis on this graph. Can you imagine how the picture will look like in your head? Just think a little bit. I'm sure you may have it. Okay, then now let's see it, if you had the right picture in your head. Mathematics is beautiful, is that right? Makes you fly. If it is taught correctly and if it is learned correctly. Now look at that. This is the graph comes out of it after you push that one there. Look at this one. Now, what do you notice the relation between these two graphs? In one sense they are same, in another sense they are kind of inverse of another. Exactly like what we started the first lecture. 3 plus 2 equals to 5, and 5 minus 3 equals to 2. They are same in a sense of equality, but they are inverse of each other with respect to addition and subtraction. Because one of them is using addition, the other one is using subtraction. So look at this one. These two are same, as you see, we rotate and reflect. But they are mirror image of each other. Now, what will be the mirror? When you say mirror image, you have to have the mirror to begin with. The mirror will be the 45-degree line. Another name for 45-degree line is y equal to x. They call it identity function. You follow me? Now, with respect that I dotted with a red line, now you can see very nicely that they are mirror image of each other. So if you look at this one, if you are standing this side, you will see this, and if you are standing this side, you see this one, all the way. Now, the advantage of using this one to discuss about the inverse of a function is that this one has geometrical justification. This has a geometrical proof for that we are going to cover it in coming lecture, or maybe another lecture, fourth, fifth lectures maybe. Okay, then, nothing else to say. I want to just thank you for watching, and as usual and as always, I wish you all prosperity and good health, and please stay safe. And until coming the next video, stay safe, not just until coming next video, but always. So long.